In this short video, our goal is to define L2 of I where the functions could possibly be complex valued. To do this, we first need to define what norm and inner product are on a complex vector space. And the definition has only one slight twist, which you will understand in a moment. Let V be a vector space over the complex numbers. A function, which we will denote by the same notation we use for inner product, from V cross V to C is said to be a complex or Hermitian inner product on V if it satisfies condition 1 dot comma V and V comma dot are linear and conjugate linear respectively. What does this mean? Well, the linearity part is rather easy to say. What it means is for all V in V and U comma W in V, we have U plus W comma V is UV plus WV as expected, and similarly V comma U plus W is VU plus VW as expected. And we also have for all C in the complex numbers, CU comma V is CU comma V again as expected. And the twist comes, this conjugate linearity twist comes in this portion. When you write U comma CV, you actually get C conjugate UV. Okay, so if you fix the second slot, what you get is a linear mapping from V to C. On the other hand, if you fix this first slot, what you get is not quite linear, because when you multiply by a complex scalar, what comes out is the conjugate of that complex scalar. Such things are known as conjugate linear or antilinear or something like that. Okay. Now, this was the first property. Now, you should convince yourself that this is not so unnatural, because you must be familiar that in Cn, if you take two vectors z1 to zn and w1 to wn, then the standard inner product on Cn of z comma w is z1 w1 conjugate plus z2 w2 conjugate plus dot 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 zn wn conjugate. So this is a standard inner product on the complex space Cn. Now observe that for this standard inner product on Cn, when you interchange the role of W and Z, what you get is W1 Z1 conjugate plus dot 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 Wn Zn conjugate, which is not quite equal to inner product Z comma W, but it's rather equal to the conjugate. Okay, so this motivates the second property. We have inner product ZW equal to inner product WZ conjugate. Now once you put this condition, this is sort of like conjugate symmetry. Once you put this condition, it becomes clear that if Z is in the vector space V, then inner product ZZ has to be a real number. Why is this the case? Well, observe that when you interchange Z comma Z, you are supposed to get ZZ conjugate by the conjugate symmetry condition, which means that the inner product of Z and Z is a complex number whose conjugate is itself, therefore it must be real. Okay, and the third condition, as you can expect, is that inner product ZZ must be greater than or equal to 0, and equal to 0 if and only if z is equal to 0. So these are the three conditions that are there in the definition of a complex inner product. They sort of mirror the three conditions that we had for a real inner product space. Okay, now a trivial fact that you can check, if V is a complex inner product space, then defining norm V to be equal to inner product VV, we get a norm on V. So using a complex inner product, you get a norm. So this will involve proving things like Cauchy-Schwarz inequality and all that for complex inner product spaces, and the proofs are very similar. The proof is very similar to what we have done for real inner product spaces. Little bit of twisting around needs to be done to take care of the conjugate linearity and conjugate symmetry, and it's not really that hard. Okay, now that we have a definitions of complex inner product spaces, we can define a norm. One second. We can define a norm on L2 of I where the functions are now allowed to be complex valued. Well, the definition is as follows. Let f comma g be in L2I complex valued, then as we have seen before, it is not hard to see that AF plus BG is also in L2I, where A comma B are now complex numbers, and F into G is in L of I. Okay, so these two are left for you. They are easy, straightforward checks. Look up the proofs of what we did for the real valued case in the last few videos and adapt the arguments to the complex valued case. You will get F comma AF plus BG is in L2I, and so is the product FG. Okay, so you define the inner product of F comma G to be, by definition, integral of FG conjugate. In fact, I should say FG conjugate is in L of I. So check that this is satisfied, that integral FG conjugate over I is well defined. And of course, norm of a vector F would be just integral of mod F squared over I. Okay. Now, the fact that mod F squared is going to be in, one second, this is whole power half. How did I forget that? So, the fact that this is well defined will follow in exactly the same way you did for the real valued case. So, and this all the properties of a complex inner product will be satisfied with the one standard exception. It need not be true that norm F is 0. It may not be true that inner product F comma F is 0 if and only if F is 0. This need not be true. What will happen is, if you can have functions which are almost everywhere 0, such that what will happen is the inner product will still be 0, but the function is not identically 0. Okay, so as I mentioned before, the Cauchy-Schwarz inequality and the triangle inequality are both satisfied in this scenario as well, because this definition gives an inner product. So now what we are going to do is, we are going to show in the next videos that L2 of I, now complex valued, is sort of complete in this norm. Complete in this norm. In this semi-norm, to be precise, because all properties are not there. The property that norm f equal to 0 implies f equal to 0 is not true. So we will show that L2 of I is actually a complete metric space. This is a course on real analysis, and you have just watched the video on norms and inner products on complex vector spaces.